All right, in example 4, we have a rectangular tank that is 3 feet wide, 4 feet high, and 6 feet long. So 3 feet wide, 4 feet tall, and 6 feet long. Okay. It contains 2 feet of linseed oil. You know what? I think I'm getting ahead of myself. I don't think I actually believe that. Weighing 58.5 pounds per cubic foot, and 2 feet of water, weighing 62.4 pounds per cubic foot. We want to figure out how much work is done if we have to pump all of the liquid to a height 2 feet above the tank. Okay, so I do think I was getting ahead of myself. The water is heavier, so it will be on the bottom. It weighs 62.4 pounds per cubic foot. The oil is going to be on top, and it weighs 58.5 pounds per cubic foot. Okay, so we want to figure out how much work is done if we have to pump, let's say, somewhere up here, another 2 feet up. Whatever, there's some other thing that we're pumping up over the edge of whatever's going on. We have to pump it to here, and then we don't care what happens after that. Maybe it just flows out, whatever, but that's where we have to get to. Okay, so first thing to notice here is that because we have 2 different densities, 2 different fluids in here, we're going to have to set this up in 2 different pieces. So let's just work on the linseed oil for starters. Within that, one thing that's really important is people want to visualize this as like I stick a hose down to the bottom and I siphon everything up from the bottom. That's not how we're going to do this. We're going to try and do this more efficiently. That makes us lift every single bit of oil the largest possible distance. So we want to imagine that the top layer gets lifted only from the top, the middle layer gets lifted from the middle, and only the bottom layer has to come all the way from the bottom. So you could imagine that we have some sort of floaty thing. I don't know if you've seen them. They have these big floaties when they're sucking oil off the surface of water. It sucks from the top, and as the fluid level drops, it drops as well. So everything's lifted from the height it's at. Okay, I think I said I was going to start with oil, but I actually was being backwards again. What I was thinking in my head is I wanted to start at the bottom, but it doesn't matter which one you start with, really. So if I'm going to imagine that this is my slice, I know it's a big rectangle. I know that some of the dimensions, all of the dimensions pretty much, are fixed. So it's always 6 feet long, it's always 3 feet wide. And then we get to name the thickness of our slice whatever we want. So I'm going to call it a delta H. Oh, and I'm not being good about explaining why I'm slicing the way I'm slicing. So in this problem, with the exception of the fact that the top and bottom are different, if we're looking at the bottom half, if we're looking at the water, the density of the water isn't changing. So no matter where we take the slice, it should have the same weight. What's changing is the distance we have to lift it. So we're going to slice so that everything is at the same height, so that it all has to lift the same distance. Okay, so if I'm calling the thickness of my slice delta H, then H better be a vertical variable, and this is another one of those where you have quite a few choices. I'm going to go ahead and say H is how far above the bottom of the tank I am, but it would be equally valid to try and say H is how far from the top of the water, or how far from the top of the tank, or how far from the very top to where we have to lift it to. Any of those will work nicely, so take your pick. Choose what seems like an easy fixed point in the tank and just stick with it, and as long as you build everything around that, it will be correct. Okay, so let's see, what do I need? So I need force times distance. So let's first work on the force. I'll call it F sub I. So the force is going to be the weight of my slice. Anytime you're lifting something up, its weight is going to be your force. You have to push that much against it to lift it. So the weight of my slice, I know that the mass density, it's not mass density, the weight density of water is 62.4 pounds per cubic foot. So if I want to know its total weight, I'm going to need to multiply by its volume in cubic feet, and then I'll just be left with pounds. The volume of this slice is 6 by 3 by delta H cubic feet. So, and this is what we were saying before. Oh man, hold on, let me make sure I got my calculator ready. I'm going to be lazy and calculator this so you don't have to wait for me to try and do arithmetic. 62.4 times 6 times 3 is 1,132 nope, I'm backwards, 23.2 delta H pounds. So I mentioned earlier that the weight shouldn't change as you went up or down, with the exception of when you cross over that water-oil boundary, that'll change. But otherwise, any slice of water is going to have the same total weight, and any slice of oil is going to have the same total weight. So there's the weight of a single slice. If I look at that slice, you don't have to do this in all these little pieces, but just so you can see them all. Distance that I have to lift it, it has to go from where it is all the way up to the top of my picture. So there's more than one way to piece this apart, but I think the easiest way here would be just to recognize that we have that total height from the bottom of the tank to the top of where we need to get the water. That's 6 feet. So if we just want to figure out this distance right here, so we'll call that an h sub I, it's going to be 6 minus h sub I feet. So the work, W for work, not for weight in this one, is going to be 1,123.2 delta H multiplied by 6 minus h sub I. I'm going to save that delta H until last. And notice that that will have units, feet times pounds, which is exactly what we're hoping for work. So if we want the total amount of work, so this is only for the water part, the work equals the integral from, okay, so again, remember, this is where people start to get some confusion. They want the distance that you lifted to show up in the limits of integration, and that's not how it works. I've already incorporated the total distance of 6 feet in the distance part of this. So the slicing, the limits of integration, tell you which H values you want to consider. So basically the slicing tells you where there is water to be lifted. So if we start at H equals 0, and we stop at H equals 2 feet, remember the whole tank is 4 feet tall, but it's only 2 feet of water, that should give us all the slices of water that we need. And I'm going to move this back a little. I'm going to put the 1123.2 out in front. And then we're just integrating 6 minus h dh, which is going to give us the 1123.2, and this is a terrible plan, equals 1123.2 times 6h minus h squared over 2. We want to go from 0 to 2. So the 0 is going to leave us with nothing. So let's see what 1,132, nope, 23.2. Oh my goodness, I have a very strong urge to have dyslexic moments with this one. 6 times 2 minus 2 squared, 4 over 2 is 2. Okay, so we've got 12 minus 2 in the parentheses. So we're going to, that's a nice one actually. That one wasn't such a bad non-calculator one. Okay, so to lift the water, we do 11,232 foot-pounds of work. To lift the oil, let me see if I can pick a different color. No. Oh. I always have my phone go off in the middle of these. Okay, so for the oil, we're going to have a slice up here. And it basically looks exactly the same, right? It's the same as this. So it's 3 by 6 by delta H. So the force part is exactly the same. Well, no, I'm getting ahead of myself again. The force part is not exactly the same. The volume part is exactly the same. 6 times 3 times delta H. But now we have to multiply it by 58.5 times 18 delta H. 58.5 times 18 is 1,053. Delta H, and what was this, 4 pounds. Okay, so slightly different calculation, but not a lot different, just a different density. I'm going to go ahead and use the exact same variables. If I'm using the exact same variables, then the distance is the same. So looking at my yellow slice, h sub I would be from the bottom. If I need to lift it all the way up to here, that's still a grand total of 6 feet that I have to subtract h sub I from. So the d sub I is still a 6 minus h sub I feet, which means that for the oil, the work done is going to be 1,053 times the integral from integral of 6 minus HDH. And then we do have to be careful about our slicing. So now, to make sure that we're getting only the oil and not the water, I've left my H variable the same, so I want it to start at 2 and stop at 4. So this is going to turn into a 1,053 times 6h minus h squared over 2 from 2 to 4. Okay, so what are we going to get in there? We're going to get 24 minus 8, which is 16. And then when we plug in the 2, we're going to get that 12 minus 2, which is 10. So we're getting 1,053 multiplied by 6, which is 6,318 foot-pounds of work. So our final answer here, go back to blue, putting this together, is, how lazy do I feel? I feel really lazy. I asked my calculator, 17,550 foot-pounds of work lifting all of the fluid to that height 2 feet above the top of the tank. Thanks for watching.